Hello, I'm Timos Ampelikiotis. Today I want to present you how to transparently run application on hypervisor and hypervisor-less systems with Virtio-Loopback. I'm working on virtual open systems as an engineer of embedded system and virtualization technologies. I was also the main developer of Virtio-Loopback project. This presentation targets to familiarize the readers with how to run application using Virtio-Loopback transparently on hypervisor and hypervisor-less environments and help them to build their own demos and drivers. The presentation includes three main parts: a description of Virtio-Loopback design and latest updates, a guide with detailed steps of how to build and run Virtio-Loopback with VST-User BLK and VST-User input devices. We will conclude this presentation with the next steps and the further development on this design. A brief description of the approach. Virtio-Loopback introduces a new hardware abstraction layer based on Virtio subsystem. It gives the ability to host user space application to take advantage of user space driver based on VST-User protocol. This approach aims at building an interchangeable execution environment between vehicle, cloud, edge, servers, developer workstation, continuous integration infrastructure, etc. Benefits of this design are that applications built for Virtio can be executed in hypervisor or non-hypervisor environments with user space drivers. The applications and the driver are decoupled. In essence, the driver could be potentially executed in another computer unit. Existing user space implementation and hypervisors can be reused. The whole design is based on a zero-copy principle, which means that no data are copied through the whole exchange process. The following link points to the referenced presentation. The new design introduced two main components, a kernel driver and a user space application. These two components combined give us the glue code to reroute all the communication and data traffic between Virtio drivers and VST-User devices. More in detail, the kernel space component is actually a new Virtio transport layer which forwards all the read and write commands in the user space where the device is implemented. The second component is an application in user space called adapter that actually it's important mainly to set up the whole system configuration and does not impact at all during the data plane. In the next slides we are going to spend some time to describe the Linux communication mechanisms used between all the components. As we see, between the adapter and the driver, Linux mechanisms are the system calls and event FDs. Later, between the adapter and the VST-User device, we use a Linux socket and event FDs to trigger notification back and forth and exchange messages. Lastly, between the device and the driver, we use system calls as the map and event FDs in order again to trigger when the new data has been arrived or consumed. We will continue by describing the building process of all the components. In the next slide we'll introduce a guide with all the required steps in order to clone and build all the Virtio-Loopback components. We will start by describing the building process of VST-User devices such as RNG, BLK and input. VST-User device implementation can be found under the QEMU project. As a result of that, we are able to extract these binaries by just building the QEMU project. To do so, we need to clone the modified version of QEMU under the VOSIS URL, check out to the correct branch, enable the VST-User BLK build flag, configure and build QEMU with the configure and make commands. So Small note on that slide, we paste the path of all the produced binaries we are going to use later in this presentation. The building process of the adapter is fairly simpler than the previous one. We just need to clone the source code, check out to the correct branch, and call the make command in order to build it. There is one important flag called arc, which help us define which are going to be the desired binaries architecture. Also, there is another flag called debug, which help us enable secondary logs in order to help the developers and a user to understand a bit more in detail the execution flow of the adapter. Last component to build is the Virtio-Loopback transport driver. We continue with the same exact process. We clone the corresponding repository, we check out to the Virtio-Loopback RFC branch, and we call the make commands as before. We get the two known arguments, arc and debug. The only difference here is that if we want to cross-compile it, we need to define our own cross-compiler. All the repos that mentioned in the previous slides can be found under the Virtual Open System GitHub server. There you're also going to find a guide of how to test and run Virtio-BLK demos, architectural documents, benchmarks, and Yocto patches for AGL. We will continue with the description of all the required steps that needed to run a simple demo for ViosUser-BLK and ViosUser input devices, and after that we are going to provide two video demos for both devices. For running ViosUser-BLK demo, we need first to create a new temporary disk image by using the dd command. We chose a block size of 4 kilobytes and 400,000 blocks. After that, we insert the loopback driver and we run the ViosUser-BLK by providing the socket path and a block source file, which is going to be the previously created disk image. Lastly, we run the adapter with the same socket path. We define the device that we want the adapter to create, and optionally we can define the queue number and the queue sizes. We will continue with the description of the demo and later the video. The following video will demonstrate in practice all the steps that we described before. We start by creating the disk image file with the dd command and then provide that as a source to the ViosUser-BLK device. The target of this demo is that the Virtio-BLK driver to create another device node which points to the very same data as our source disk image file without the need of any copy. Now let's go on and see the video. As we shown in the slide, we're starting by inserting the driver. Next, we need to run the ViosUser-BLK device, providing the correct socket path and block source file. And lastly, run the adapter by providing the corresponding socket and the correct device type. As we see in this part of the video, a new block device is being created by ViosUser-BLK. We try to mount it and we see an already existed file inside it which is empty, and we try to write something simple inside it just to do a simple test. Then we verify that this is actually written, and we go on with unmounting the drive, mount it again, and verify that all the changes are being preserved. Before starting describing the process of how to run Virtio user input, we need to give some more details about the if test command, which is basically shows the event logs of an event file. By using this command, we try to understand which event file is the corresponding one to our external mouse. Then we go on with inserting the Virtio-Loopback transport driver, running the Virtio user input by providing the no-grab argument, which gives the ability to Virtio user input to not grab exclusively the event file, the correct socket path, and the source event path, which points to the event file found earlier by using the if test command. Last step again, it's always to run the Virtio-Loopback adapter with the correct socket path and the type of our Virtio user device. Next, we'll follow a description of the video demo and the target of it. Again, this video demo will describe all the steps that has been shown before. Starts by sourcing an event file to the Virtio user input. This source file prints all the event logs coming from an external mouse. After all the initialization process is being in place, we expect from Virtio input to create another device node, let's say event Y, which prints the very same data as the event X that we sourced initially to the Virtio user input device. Then we are going to verify if both of these files print the same logs. As described in the slides, we start by looking on which is the event file corresponding to our mouse events, and we find out that this is the event file 3. Then we start the Virtio user input device with the same event file and socket path, inserting the driver, and go on by running the adapter with the corresponding socket path and the device type. After that steps, the only thing that remains is to verify that a new event file is being created. And this file gives us the exact same logs as our short event file. In this case, event file 3. More demos for Virtio-Loopback can be found in Vos's web page. We'll leave the link down below, and new demos are going to be added in the next months. Next steps and further development on Virtio-Loopback is going to be to add support for more Virtio devices. For reference, Virtio GPU, Virtio Sound, CAN, GPIO, console. After that, we plan to design a new solution for using Virtio-Loopback in the context of multiple ECUs. As we said in the beginning, Virtio-Loopback provides a fast and reliable solution as a hardware abstraction layer between Virtio driver and user space devices. To summarize, it's based on a zero-config principle, has no modification on Virtio source code, and has only slight modification on Virtio user library, which are going to be eliminated in the future. There is room for performance and compatibility optimizations, such as the memory mapping mechanism, which is used to deliver the data from the kernel space and share them to the user space where the device lives. Another possible optimization would be to make Virtio-Loopback fully compliant to the existing Virtio user protocol without any need of modifications. Support for more devices in Virtio-Loopback, as said before, is going to be added in 2023. Thank you a lot for watching. We are going to be very happy to answer any of your questions to the following email address.